You'll get a lot of questions about projectile motion when you study 2D kinematics. It is really just the path something takes when you throw it in a gravitational field. You give it an initial velocity, which means some speed and some angle, and gravity's pulling it down, and it makes a path kind of like this. We can draw the initial speed, vi, at some angle theta. So we have an initial vector velocity, and it's going to make a path kind of like that. Up and down makes a parabola. So what we want to do now is calculate a few properties of projectile motion. Maybe worth memorizing, maybe not, but either way it's good to see them derived. Helps us understand projectile motion. So our initial thing we are given is usually a speed and an angle. So often one of the very first things you want to do is think about breaking that up into its two components. So there's a vi cosine theta is the x component, and a vi sine theta is the y component. We're just breaking that up into x and y, because you always think about those independently when you do a projectile. Often you start at the origin. If it's a nice little, so it's 0, 0, x equals 0, y equals 0. The x initial is 0, the y initial is 0. Now you may do an uneven trajectory later, where that's not the case, but in this simple one we'll start that way. So we can write the position vector, always important. So let's think about our 1D kinematics for x. X initial is 0, Vx initial right here. So we could say Vi cosine theta t, and then the acceleration of the x is 0. So that's really the whole thing. I hat. And now we want to write the 1D kinetics for y. Y initial is 0. The velocity is vi sine theta t. And then we have the acceleration of the y minus 1/2 gt squared. J hat. There we go. And you can kind of see why it's a parabola. It's sort of parametric, but you can see as you march across x in time, this t squared term is what makes you have a parabolic trajectory. But it's really not the geometrical shape of the trajectory we care about, it's the properties. How fast is it going, when, where does it land, etc. So we're going to calculate 3 properties of an even parabolic trajectory. Alright, so what are we going to do first? First, we're going to do the hang time. So the hang time is just the time it's in the air. I'll call it th. You know the idea of hang time, th. So how do you figure out the hang time? Well, when you work these problems, you want to have your position vector ready, and you just, when you ask something, you just look at the position vector and you say, well, how do I get it? Or maybe the velocity vector. In this case, the hang time, how do I get the hang time? Well, what's special about the hang time? It's when it launched at t equals 0 and it landed at some other time. So it's really when it lands would tell you the total hang time. So when does it land? It lands when y equals 0. So all we got to do is take this y component and set it equal to 0. All right, so we say vi sine theta t, and I'm going to call it th because we're finding a specific time, minus 1/2 g th squared. That's a specific time when this equals 0. So we just have to solve that for th. Well, let's see, we can factor out a th and get vi sine theta minus 1/2 g t equals 0. And then you see one solution is when th equals 0. And that's actually a correct solution. The y position is 0 when the time is 0. But that's not the one we're looking for. The one we're looking for is here. So if that is going to be 0, the way to solve this is you assume one or the other is 0. So if this is going to be 0, v sine theta equals 1/2 g th. So it would have to be, the 2 would come over here, 2v sine theta over g. Right? So the hang time we want is 2vi sine theta over g. Right? So let's put that one over here. We're going to put them over here as we collect them. The hang time is 2vi sine theta over g. And you can decide if you want to memorize these that we come up with or just be able to derive them when you need them. All right, so now let's look at the next one is the range. The range is how far it went in x. All right, so if we're going to label the range on the drawing, it would basically be here, this distance. Okay. Let's see, how far did it go in h? Well, let's see. Well, we already calculated the hang time, so it's really how far in x in th. So really, all you got to do is say how far did it go? What was the x position if we plug th in here? That's really all it is. So we say the range, if we plug in th for the x, that's going to be vi cosine theta, and we plug in th. 2 vi sine theta over g. And we just got to put all that together, and we'll have the range. R is 2, we got a vi squared, sine theta cosine theta, over g. Done with range. Let's see. And height. Let's see. Height, h. How high in y? Well, we could also just say, let's just use the y component, and we can, but now we got to think, we don't really want to do it at th. We already showed that if you plug in th, the hang time, you get 0. But since this is a nice uniform, even symmetric trajectory, it's in a half th. So all we really have to do is plug in a half of this value into here, and that should be the height. So let's try that. H equals vi sine theta, and I'm going to plug in vi sine theta over g. Vi sine theta over g minus 1/2 g, 2, 1/2 g, and now I want to put this squared. A half t squared is vi squared sine squared theta over g squared. Vi squared sine squared theta over g squared. And then you say, oh, that one kind of made a mess, didn't it? Well, not really. If you look, you'll notice these are kind of the same term. The difference is only a factor of a half. So they're both vi squared. See, vi squared, sine squared theta. Let's see, they're both over g, because that g over that g squared turns into 1 over g. So you've really just taken the whole value minus a half the value. So that means this is a half the value. We've got to put a t there, or 2 there. So there's h. So that's the 3 properties. So this h is right here. How long it's in the air, the hang time, th, how far it goes, the range, and then the height, how high it goes. These work for a symmetric trajectory, or projectile motion, one that starts and ends at the same height and doesn't crash into anything. Okay? If you get into more complicated ones, you can't use these directly, but understanding how they work and how we got them will help you do other problems.